The Isolator Helmet. In 1925, Hugo Gernsback introduced the world to a device that looked less like a productivity tool and more like an instrument of psychological punishment. Gernsback was not a fringe inventor operating out of obscurity. He was the founder of Amazing Stories, the first major American science fiction magazine and one of the most influential figures in early 20th century popular science. When he built the Isolator and wore it publicly, people paid attention, and what they saw disturbed them in ways they struggled to articulate. The helmet was enormous. It enclosed the entire head in a thick, padded shell designed to block out all external sound and eliminate peripheral vision entirely. A single narrow horizontal slit was cut across the front, providing only the most minimal field of sight, enough to see the page directly in front of you, and nothing else. The world beyond that slit ceased to exist. Sound did not penetrate the shell in any meaningful way. Light entered only through that one controlled opening, and because sealing a human head inside an airtight chamber creates an obvious biological problem, the helmet was connected to an external oxygen tank that fed breathable air directly to the wearer. Gernsback published photographs of himself wearing the device and claimed with complete seriousness that it increased his productive output by 300%. He framed it not as an experiment, but as a solution. Modern life, he argued, was saturated with distraction. The human mind was not built to filter the constant noise of industrial civilization. If the environment could not be made quiet, then the individual had to carry their own silence with them, sealed inside a personal chamber of focused isolation. The concept was not scientifically baseless. The principles Gernsback was working from, that sensory reduction improves concentration, that distraction is neurologically costly, that controlled environments produce measurably better cognitive performance, have since been validated extensively by modern research. Sensory deprivation studies conducted from the 1950s onward confirmed that reducing external stimulation can produce significant improvements in focus and creative output under the right conditions. But the Isolator terrified people. Photographs of Gernsback sitting at his desk, head encased in that massive, expressionless shell, connected to an oxygen supply, produced a reaction closer to horror than admiration. It felt wrong in a way that was difficult to name. A person rendered faceless, breathless, without mechanical assistance, reduced to a narrow slit of perception. It was a vision of productivity that looked indistinguishable from imprisonment. The helmet was never manufactured commercially. It appeared in a single issue of Science and Invention magazine and quietly disappeared. But the problem it was trying to solve never disappeared with it. Noise-canceling headphones operate on the same principle. Sensory deprivation tanks charge premium rates for the same experience. Focus applications replicate the same logic digitally. Gernsback built the Isolator a century ago. We are still building versions of it today. We just made them smaller and considerably less terrifying. The Electric Corset. Before the modern wellness industry sold infrared saunas and electrical muscle stimulators, Victorian women were being fitted with voltage. Not metaphorically, literally. In the 1880s, a product called the Electric Corset entered the commercial market with the kind of confidence that only an era of unchecked scientific enthusiasm could produce. It was advertised in mainstream publications, endorsed by figures presenting themselves as medical professionals, and purchased by thousands of women across the United States and Britain who had every reason to believe they were investing in their health. The design was straightforward in its audacity. A standard corset, already a garment of considerable physical consequence, was threaded with fine metallic wiring designed to generate and conduct static electricity across the torso. The current was low, the mechanism was passive, and the science behind it was almost entirely fabricated. But the claims made on its behalf were extraordinary. Manufacturers promised improved circulation. They promised corrected posture. They promised relief from fatigue, nervous disorders, digestive complaints, and a condition the medical establishment of the time called hysteria, a diagnosis so broad it functionally meant anything a physician wanted it to mean. The reality was considerably less transformative. Women who wore these garments reported mild tingling sensations, occasional sharp shocks when the wiring shifted against the skin, and during summer months, uncomfortable overheating caused by the metallic components absorbing and retaining heat. There is no documented clinical evidence that the electric corset produced any of the physiological effects its manufacturers claimed. What it produced, reliably, was profit. This was not a fringe product sold in the back pages of obscure catalogs. Electric corsets were prominently featured in department store displays and mainstream newspaper advertisements. They were positioned alongside legitimate medical goods. The word electric alone carried enormous cultural weight in the late 19th century. Electricity was new. Electricity was powerful. Electricity had transformed communication and was beginning to reshape industry. If it could do all of that, the logic went. Surely it could do something remarkable inside the human body as well. That logic was not irrational, given what ordinary people understood about science at the time. Galvanism, the study of electrical stimulation in biological tissue, had been a serious field of inquiry since Luigi Galvani's experiments in the 1780s. By the 1800s, genuine medical researchers were exploring electrical stimulation for muscular conditions. The electric corset manufacturers understood exactly what they were doing. They borrowed the language and the credibility of real science and applied it to a product that had none. What the electric corset actually reveals is not ignorance. It reveals the persistent human instinct to believe that new technology can perfect the body. That instinct produced the electric corset in 1885. It produced magnetic therapy bracelets in the 1990s. It produces wearable biometric devices today. The packaging changes. The voltage changes. The belief never does. If this is the kind of buried history nobody talks about, you are in the right place. Subscribe and hit the bell. We are just getting started. The atmospheric railway. In 1847, a stretch of railway line along the South Devon coast began operating without a single engine car. No locomotive, no coal tender, no visible source of propulsion whatsoever. Passengers climbed aboard, the signal was given, and the train moved. Smoothly, quietly, and with a speed that surprised everyone who witnessed it. To observers standing along the trackside, it appeared to violate something fundamental about how the physical world was supposed to work. A train was moving, and nothing was pushing it. The system had been designed and constructed by Isambard Kingdom Brunel, one of the most accomplished engineers of the 19th century, in collaboration with the atmospheric railway pioneers Samuda and Clegg. The principle behind it was elegant in its simplicity. Between the rails, a continuous cast iron pipe, roughly 15 inches in diameter, ran the entire length of the line. Inside this pipe sat a piston connected to the undercarriage of the train above, through a longitudinal slot cut along the top of the tube. Stationary pumping stations positioned at intervals along the route continuously evacuated the air from the pipe ahead of the train. The atmospheric pressure behind the piston, now greater than the near vacuum in front of it, pushed the piston forward. The train followed. No combustion, no moving engine, just the invisible weight of the atmosphere doing the work. The results, in controlled conditions, were remarkable. The South Devon Atmospheric Railway achieved speeds of around 68 miles per hour during trials, which was exceptional for the period. The ride quality was noticeably smoother than conventional steam trains because there was no engine vibration transmitted through the carriages. The system produced no locomotive smoke inside tunnels or stations. Operating costs, in theory, were lower because the stationary pumping engines could be run more efficiently than individual locomotive boilers. Brunel committed to the project with characteristic confidence. The collapse came from a detail so mundane it bordered on humiliating. The longitudinal slot in the top of the pipe had to be sealed to maintain the vacuum, and the material chosen for this seal was leather, greased with a mixture of tallow and lime soap to keep it supple. The leather flap worked adequately in mild conditions. It did not work in the climate of southwestern England. The combination of salt air, moisture, frost, and the particular appetite of the local rat population destroyed the seals systematically and continuously. Maintenance costs escalated beyond any projection. The leather deteriorated faster than it could be replaced. Within less than a year of full operation, the system was abandoned entirely. Brunel publicly acknowledged the failure, absorbing significant professional damage in the process. The atmospheric railway became a historical footnote almost immediately. But what it described was not a dead end. It was a working demonstration of vacuum-assisted transit more than a century and a half before Hyperloop concepts entered public conversation. The principle was sound. Only the materials fail. Sometimes the idea arrives before the world is ready to build it properly. The Telautograph. In 1888, Elisha Gray filed a patent for a device that could transmit handwriting across electrical wires in real time, not typed text, not coded signals requiring translation. Actual handwriting, the specific pressure of a pen against paper, the particular angle of a signature, the fluid motion of a hand drawing a diagram, all of it captured, converted into electrical impulses, transmitted across distance, and reproduced on the receiving end by a mechanical stylus moving in precise coordination with the original hand. Gray called it the Telautograph, and it worked exactly as described. Gray was not an unknown figure operating at the edges of American invention. He had filed a patent caveat for a telephone design on the same day Alexander Graham Bell filed his telephone patent in 1876, a coincidence that produced one of the most contested intellectual property disputes in the history of American technology. Bell was awarded the patent. Gray was not. The Telautograph was, in some respects, Gray's vindication, a device that Bell had not imagined and could not claim, and one that solved a problem the telephone explicitly could not. The telephone transmitted voice. It could not transmit a signature, a map, a prescription, a technical diagram, or any information that existed in visual rather than verbal form. The Telautograph filled that gap precisely. The sending unit tracked the movement of a stylus through a system of rheostats that converted horizontal and vertical motion into varying electrical resistances. Those varying resistances traveled along telegraph wires to the receiving unit, where a corresponding mechanical arm interpreted the signals and reproduced the movement with a pen on paper. The synchronization between sender and receiver was achieved through a continuous electrical connection that updated in real time. The Gray Telautograph Company was established in 1888, and the device entered commercial use through the 1890s. Adoption was genuine and widespread in specific industries. Railroad companies used telautographs to transmit written orders between stations, eliminating the transcription errors that plagued Morse code communications. Hospitals used them to send prescriptions and patient instructions between departments without requiring physical delivery. Banks adopted them for transmitting signatures for verification purposes, recognizing that a reproduced signature carried evidentiary weight that a typed name did not. The device remained in active commercial use far longer than its historical obscurity suggests. Updated versions of the Telautograph were still operating in some institutional settings as late as the 1970s. Nearly a century after Gray's original patent, its disappearance from public consciousness was not a sudden collapse but a gradual displacement, first by early fax technology, then by digital transmission systems that could handle visual information more efficiently. But the fundamental mechanism Gray invented in 1888, translating physical stylus movement into electrical signals and reconstructing that movement remotely, is precisely the principle behind every digital pen, every touchscreen, and every robotic surgical system that allows a surgeon's hand. Movements to be replicated by instruments operating at a distance. Gray built the first version of all of it. In a different timeline, his name sits beside Bell's in every history of communication technology. In this one, almost nobody remembers him. The electric pen. In 1876, Thomas Edison introduced a device so ahead of its operational context that the world had no adequate infrastructure to support it. The electric pen was not a pen in any conventional sense. It was a handheld motorized instrument powered by a small wet cell battery, containing a needle that reciprocated at approximately 50 strokes per second, driven by a miniature electromagnetic motor housed in the upper portion of the device. When pressed against paper and moved in the normal motion of handwriting, the needle perforated the sheet continuously, leaving behind not ink, but a precise pattern of tiny holes that traced every curve and line of whatever the user had written or drawn. The perforated sheet then became a stencil. Placed over a blank page and rolled with an ink-saturated roller, it transferred an exact reproduction of the original handwriting onto the surface beneath. Remove the stencil, reposition it, roll again. The same document reproduced with complete fidelity, as many times as required. Edison's promotional materials claimed the device could produce up to 5,000 copies from a single stencil without meaningful degradation of quality. Edison was 29 years old when he patented the electric pen. He was already operating his Newark laboratory with commercial intent, and he understood the market he was targeting precisely. American businesses in the 1870s faced a genuine and costly problem. Every duplicate of every document had to be produced by hand. Copying clerks were a standard feature of any substantial commercial operation, employed specifically to reproduce correspondence, contracts, and records through manual transcription. The process was slow, expensive, and introduced errors. Edison's electric pen promised to eliminate the copying clerk entirely. The Western Electric Company licensed the device and pushed it into the commercial market with significant investment. It sold. Thousands of units moved through the late 1870s into businesses across the United States and Britain. But the practical experience of operating the device revealed frictions that Edison's promotional enthusiasm had not fully addressed. The wet cell batteries required regular maintenance and produced corrosive acids that damaged surfaces and clothing. The needle mechanism required precise calibration to perforate cleanly without tearing. The device produced a persistent buzzing sound during operation that users found wearing over extended periods. Adoption plateaued and then contracted. Edison himself moved on. He licensed the stencil technology, which eventually evolved into the mimeograph machine, and directed his attention toward projects that would define his legacy more visibly. The electric pen was quietly retired from his personal catalog of achievements. What followed it into history, however, was not the mimeograph. In 1891, Samuel O'Reilly examined the mechanism of Edison's electric pen with specific attention to its reciprocating needle and electromagnetic drive system. He modified the design, substituted ink for the perforation function, and patented the first electric tattoo machine. The device that Edison built to duplicate office documents became the instrument that has since permanently marked hundreds of millions of human bodies. Edison intended to mechanize paperwork. He accidentally mechanized one of the oldest art forms in human history, the human-powered car. In 1869, long before the internal combustion engine had established its dominance over personal transportation, a French engineer named Jean-Joseph Tien Lenoir built a vehicle that moved entirely through human mechanical effort. No steam, no gas, no external fuel source of any kind. The vehicle was propelled by an occupant operating a system of pedals and levers connected to a crankshaft, which transferred mechanical energy to the wheels through a series of gears and drive components. It was simultaneously a carriage, a bicycle, and an experiment in whether human muscular output could substitute for the combustion and steam technologies that were rapidly reshaping European industry. Lenoir was not a marginal figure in the history of engineering. He had already made a significant contribution to mechanical history in 1859 when he developed one of the first functional internal combustion engines to achieve commercial application, a gas-powered engine that preceded Nicolaus Otto's more refined four-stroke design and was used to power small industrial machinery across France and Britain. Lenoir understood combustion intimately. His decision to build a human-powered vehicle was therefore not born of ignorance about available alternatives. It was a deliberate design choice rooted in specific practical considerations about fuel availability, mechanical simplicity, and operational cost. The vehicle Lenoir constructed was closer in its mechanical architecture to a velocipede than to the horse-drawn carriages that dominated French roads. The frame was heavier than a conventional bicycle of the period, built to support the weight of a passenger compartment, and the drive mechanism was more complex, routing human pedal effort through a crankshaft arrangement that provided the torque necessary to move a substantially heavier load than a single rider on two wheels. It was not fast. Contemporary accounts suggest it achieved speeds of several kilometers per hour under optimal conditions, which placed it roughly in competition with a brisk walking pace. On inclines or rough road surfaces, performance degraded considerably. The vehicle never entered commercial production. It existed as a functional prototype, demonstrated publicly and documented in engineering literature of the period, but it attracted no investor interest sufficient to develop it further. The internal combustion engine was already generating commercial momentum, and the economic logic of fuel-powered transportation made human-powered alternatives appear primitive by comparison. Lenoir's pedal car was catalogued as a curiosity and largely forgotten within a decade of its construction. What makes it historically significant is not its performance, but its timing and its premise. Lenoir built a zero-emission personal vehicle in 1869, more than a century before environmental concerns about combustion engines entered mainstream political discourse. The engineering problem he was solving, how to move a person from one location to another without burning anything, is precisely the problem that electrification, hydrogen fuel cells, and human-powered vehicle research are working to solve today. The Velomobile, a fully enclosed human-powered vehicle capable of highway-adjacent speeds, is a direct conceptual descendant of what Lenoir built. He arrived at the question before the world understood why the question mattered. The thermoelectric fan. In the 1880s, while the rest of the industrialized world was racing toward larger engines, heavier machinery, and more aggressive consumption of coal and steam, a quieter category of invention was being developed in European workshops that operated on an entirely different principle: not more power, less. The thermoelectric fan required no electrical grid, no battery, no fuel reservoir, and no external mechanical input of any kind beyond a single small flame. It sat on a surface, absorbed heat from beneath, and produced a continuous rotating motion that moved air. That was the entirety of its operation. A flame went in. A breeze came out. The scientific principle making this possible had been documented decades earlier. In 1821, German physicist Thomas Johann Seebeck discovered that when two dissimilar metals are joined at 2 points, and those junctions are maintained at different temperatures, a continuous electrical voltage is generated across the circuit. The greater the temperature difference between the two junctions, the greater the voltage produced. This phenomenon, subsequently named the Seebeck effect, established that heat differentials could be converted directly into electrical current without any moving parts, without combustion, and without any intermediate mechanical stage. The conversion happened at the molecular level, silently and continuously, for as long as the temperature difference was maintained. The thermoelectric fan of the 1880s applied this principle in its most direct and elegant form. A thermoelectric generator constructed from joined dissimilar metals was positioned at the base of the device, directly above a heat source, typically a kerosene lamp or a small spirit burner. The lower junction absorbed heat from the flame. The upper junction remained at ambient room temperature. The temperature difference between the two junctions generated a small but sufficient electrical current, which was routed to a compact electric motor connected to a fan blade. The motor turned. The blade rotated. The room received a gentle, continuous circulation of air. The devices were manufactured and sold commercially, primarily in Britain and continental Europe, during the final decades of the 19th century. They were marketed as domestic comfort items, positioned alongside other refined household goods for middle and upper-class consumers who valued both their practical function and their unusual operational elegance. A machine that produced a cooling breeze from a flame, with no wires, no batteries, and almost no sound, occupied a category that felt closer to natural philosophy than to industrial engineering. Commercial interest declined as electrical infrastructure expanded through the early 20th century. Once reliable grid electricity became available in urban homes, the complexity and cost of thermoelectric generation made it impractical compared to simply plugging a conventional fan into a wall socket. The thermoelectric fan was retired not because its principle was flawed, but because cheaper energy made its elegance unnecessary. That elegance has since returned to serious scientific attention. Modern thermoelectric generators operating on the same Seebeck principle are being developed for waste heat recovery in industrial facilities, for powering remote sensing equipment, and for energy harvesting in wearable technology. The 1880s fan anticipated all of it. It understood that heat differentials are everywhere, and that imbalance, properly understood, is not a problem. It is a resource. The Mechanical Leech. In the early decades of the 19th century, bloodletting was not a fringe practice tolerated at the margins of legitimate medicine. It was mainstream. It was taught in medical schools, prescribed by respected physicians, and administered to patients across the full spectrum of illness, from minor fevers to life-threatening conditions. The theoretical foundation was ancient, rooted in humoral medicine dating back to Hippocrates and Galen, which held that the human body contained 4 fundamental fluids: blood, phlegm, yellow bile, and black bile, and that disease resulted from imbalance among them. Removing blood was considered a direct and rational intervention, not a last resort, a first response. Natural leeches had served this function for centuries. The medicinal leech, Hirudo medicinalis, was applied to the skin of patients throughout Europe and America in extraordinary quantities. French physicians alone were importing an estimated 40 million leeches annually by the 1830s, a demand so extreme that European leech populations were being harvested toward functional extinction in certain regions. The creatures were temperamental, difficult to store, impossible to dose precisely, and prone to detaching prematurely or attaching in unintended locations. They carried contamination risks between patients. They were, by any clinical standard, unreliable instruments. The mechanical leech emerged as a direct response to these practical failures. Victorian instrument makers, working primarily in brass and steel, designed devices that replicated the essential functions of the natural leech with the precision and repeatability that characterized the finest surgical instruments of the period. The standard mechanical leech consisted of a small cylindrical brass housing containing a rotating scarificator mechanism, a series of spring-loaded blades arranged in a circular pattern that, when triggered, made multiple small incisions simultaneously across a defined area of skin. Attached to this cutting mechanism was a suction chamber, sometimes a glass cup with a manually operated or spring-driven piston, which drew blood from the incisions in controlled, measurable quantities. The instruments were manufactured to exacting standards. London and Paris instrument makers produced mechanical leeches finished to the same quality as the finest pocket watches of the era, with polished brass housings, engraved surfaces, and mechanisms that operated with a smooth, precise action. They were stored in velvet-lined cases alongside other surgical instruments, indistinguishable in their presentation from tools of unambiguous therapeutic value. Physicians who owned them were demonstrating professional seriousness. These were not crude implements. They were precision devices for a procedure that the entire medical establishment considered scientifically valid. The collapse of bloodletting as a medical practice came gradually through the middle and late 19th century, driven by the emergence of controlled clinical observation that repeatedly failed to demonstrate patient benefit and frequently documented patient harm. By the time germ theory and evidence-based medicine had reshaped clinical practice, the mechanical leech had lost its purpose entirely. What remains is the object itself and what the object represents. The mechanical leech was the product of genuine craftsmanship applied to a procedure we now recognize as harmful. It was not barbarism. It was the best available interpretation of evidence within a framework that happened to be wrong. That distinction matters because every era practices medicine at the boundary of what it knows and what it does not yet understand. The instruments always look precise. The theory does not always survive. The Pneumatic Post. In 1897, the United States Post Office inaugurated a pneumatic mail system beneath the streets of New York City that was, by every operational measure available at the time, faster than anything else moving correspondence through an American urban environment. Letters deposited at a participating post office traveled through a network of underground cast-iron tubes, propelled by compressed air and vacuum pressure, and arrived at their destination station within minutes, not hours. Not the following morning. Minutes. The system connected 6 stations across Manhattan, running beneath some of the most densely trafficked streets in the world, entirely invisible to the city above it, moving mail at speeds approaching 30 miles per hour through tubes roughly 2 feet in diameter. The technology had been developing for decades before New York's adoption. London had operated a limited pneumatic dispatch system as early as 1863, initially conceived as a means of transmitting telegraph messages between central offices faster than a messenger boy could carry them on foot. Berlin, Paris, Vienna, and Chicago all developed variations of the system through the 1870s and 1880s, each refining the engineering of tube construction, capsule design, and pressure management. By the time New York committed to a serious municipal installation, the fundamental technology was well understood and had been proven in multiple urban environments across 2 continents. The New York system at its peak extended to approximately 27 miles of underground tubing connecting 23 postal stations across Manhattan and into Brooklyn. The cylindrical carriers, manufactured from fiber and metal, were loaded with sorted mail, sealed and inserted into the tube network, where differential air pressure propelled them through the system. Receiving stations detected incoming carriers, decelerated them through controlled pressure reduction, and discharged them for immediate sorting and onward delivery. The throughput was substantial. At its operational height, the New York pneumatic system was handling approximately 30% of the city's total mail volume. The engineering vulnerabilities accumulated over time in ways that proved increasingly expensive to address. The underground tubes were subjected to the constant mechanical stress of a city above them: construction, subway expansion, the weight of traffic, and the thermal cycling of New York's seasonal temperature extremes. Joints developed leaks. Pressure differentials became inconsistent. Sections of tube were damaged by adjacent construction projects and required excavation to repair, which meant disrupting streets and suspending service on entire branches of the network simultaneously. The rat population of Manhattan's underground, as reliable a presence as any structural element, found the tube joints accessible and the interior environments hospitable. Operational costs escalated continuously, while the competing infrastructure of automobile delivery and telephone communication was simultaneously reducing the urgency that had made the pneumatic system's speed so valuable. The post office decommissioned the New York pneumatic mail network in 1953 after more than 50 years of operation. Most of the infrastructure remains underground, sealed and unused, beneath streets that have been rebuilt several times above it. The system's descendants are not difficult to identify. Hospital pneumatic tube networks move specimens and medications between departments in exactly the same manner. Drive-through banking tubes operate on identical principles. The Hyperloop concept is a scaled reinvention of the same fundamental idea applied to human passengers. The Pneumatic Post did not fail because the concept was wrong. It failed because the city grew faster than the infrastructure beneath it could adapt. The Phonautograph. In 1857, a Parisian inventor and typesetter named Edouard Scott de Martinville built a device that accomplished something no human being had ever accomplished before. He captured sound, not music in written notation, not a description of sound in language, the actual physical shape of a sound wave, as it existed in the air at a specific moment in time, preserved on a physical surface in a form that could theoretically be examined, studied, and measured. He called the device the Phonautograph, from the Greek roots meaning self-writer of sound, and he patented it in France on March 25, 1857. a full 20 years before Thomas Edison filed his patent for the phonograph. The mechanism Scott de Martinville designed was directly inspired by the anatomy of the human ear. A large horn collected and focused incoming sound waves, directing them toward a thin, flexible membrane stretched across the narrow end of the horn, analogous to the eardrum. Attached to the center of this membrane was a fine stylus, typically made from a stiff bristle. As sound waves struck the membrane and caused it to vibrate, the stylus moved in precise correspondence with those vibrations. Beneath the stylus, a cylinder coated in lamp black, the fine soot deposited by an oil flame onto paper, wrapped around the cylinder's surface, rotated at a controlled speed. The moving stylus traced the shape of the sound wave into the soot coating as the cylinder turned, producing a continuous visual record of the acoustic event occurring in front of the horn. The resulting recordings were delicate, ghost-like tracings on fragile paper, thin wavy lines of varying amplitude and frequency, readable to a trained eye as representations of acoustic patterns but entirely silent. Scott de Martinville had no mechanism for playback and, critically, does not appear to have considered playback a necessary feature of his invention. His stated purpose was scientific. He wanted to study the visual shape of sound, to create a written phonetic alphabet derived from actual acoustic waveforms rather than conventional alphabetic symbols, and to give researchers a tool for analyzing speech and music with the same visual precision available for studying light or electricity. He recorded voices. He recorded musical instruments. He recorded himself. The recordings accumulated in his Paris workshop and were eventually archived, their existence known to historians of technology, but their content inaccessible for more than a century, because no mechanism existed to translate the visual tracings back into sound. In 2008, researchers at the Lawrence Berkeley National Laboratory in California applied optical scanning technology and digital signal processing to several of Scott de Martinville's surviving Phonautograph recordings. They photographed the soot tracings at high resolution, converted the visual waveform data into digital audio files, and played them back. What emerged from a recording made in April 1860 was a human voice, female, singing the French folk song Au clair de la lune. The audio was fragile and warped, the pitch initially misidentified because the original cylinder rotation speed had been estimated incorrectly, but it was unmistakably a voice. The oldest recorded human voice in existence, captured by a machine that was never designed to speak. Scott de Martinville recorded humanity's first preserved voice and died without ever hearing it. The recording waited in silence for 148 years. It had always been there.